Let us take a look at our next question. And this question is about the object model. It's about how do we decide when to implement these data model methods, these underscore methods. Let's take a look. Our first premise is that data model methods have explanatory power. In other words, if I show you some code with a pandas series, can you tell me how to find the size of this thing? Is it .size? Is it .shape? Is it .length? Nope, that one doesn't exist. Is it .num rows? Nope, that one doesn't exist. Is it .num values? Nope, that one doesn't exist. No, you're just going to say len of s. You see that, you know exactly what it means, the size of this series, the number of entries, and if you wanted to be slightly more specific, you might say len of s.index, but because it's one-dimensional data, there really shouldn't be any difference here. Part of the power of the Python data model, of these top-level functions, these underscore methods that we implement, is to give readability, to give understandability, to give explanatory power to our code, for somebody to be able to spot that code and to understand exactly what it does. The data model oftentimes, however, has some interpreter-driven requirements that also further inform the meaning. It's not just seeing len, it's seeing len and knowing certain things that the interpreter is going to enforce on len. For example, if you had some class that represented some delta, some change, maybe as part of some reconciliation report, you might say, okay, well, this is just the before value minus the after value. But if this is negative, and you say the size of this change is just our len, so we don't have to do change.size or some nonsense like that. But if we were to implement this with len, we can see that the interpreter is going to prevent us from doing this because len has to be non-negative. If we had some event that was part of some measure space, and we wanted to say the size of this event is the probability of it having happened, and we could sum up all the events and see if they sum to unity, and see if they're an exhaustion of, they span the entire space, we might return a floating point value, except len doesn't allow us to return a non-integer value. So what we can see is the explanatory power is oftentimes moderated by us knowing that the interpreter is going to require that the data model method return a non-negative integer. Len means what is the size of this thing, where size is constrained to mean the non-negative integer size of this thing. So whenever you see len, you say, oh yeah, that's the non-negative integer size, whatever that happens to mean for my particular type. And for a series, that makes sense, the number of rows, the number of entries in the series. The data model methods oftentimes also have conventions that people generally expect. And you see this often with things like repr. Repr has a particular convention. People say that the repr should be some textual data, some Python string, and it enforces that is a string that more or less matches to the code that you wrote to create this thing in the first place. So you can see this here matches more or less exactly to this, unless there is no way for me to deterministically recreate this particular type. So for example, when we try and open a file and we look at the repr of this file object, we see that it has angle brackets before and after to indicate to us, oh no, you can't actually reconstruct this thing. So we have those conventions. Consider, however, that when we implement these data model methods, we're oftentimes also delegating this behavior to a base type or a composed object. And so it kind of makes sense that we write this repr in this fashion, calling repr within the repr. It's very often that when we implement len, we implement it in terms of length on some constituent object, or we implement len in terms of len on some base type. But these general expectations are very loose expectations. Whereas when we look at something like NumPy and we look at the repr on a NumPy and D array, it looks okay. When we look at the repr on a pandas array, this breaks every one of these conventions. So this is a general expectation. When we write these data model methods, if the interpreter is not enforcing something, we usually have a very loose expectation. Oh, this is going to do the following thing. And in the case of something simple like repr, that's something that breaks quite often. But in the case of other things like greater than or less than or EQ, there are cases where we may have a reasonable expectation that it's always going to give us something. For example, we have a reasonable expectation that getItem is going to give us some constituent object, it's not going to give us some random value. We have a reasonable expectation that getItem is not going to clear out the contents of some container. Here's another premise. Data model methods must be unique, and they cannot encode modalities. So they have to be unique with no capacity for enabling modalities. Here's what I mean. When you write len on an object, this is the one unique way to implement len. You can't have len under one condition and len under another condition. We don't have C++ style overloading where you can pass in different arguments. In fact, for many of these data model methods, we can't even pass in any arguments at all. For most of them, we generally can't pass in any, for all of them, we can't pass in any modal parameters. For almost all of them, I have to really think if that's the case for all of them. For all of the common ones, we can't even pass in modal parameters. We at most can pass in data parameters. Consider, when we write a underscore method, we're trying to determine, or we're trying to write this to assert, to lean into the ability for this code to be more explanatory, this code to be more readable. And what gives us explanatory power is when we read some code and it's unambiguous on what it means. Len of object. That means the size of the object, and I know exactly what you mean by the size, the non-negative integer size of this object, I know exactly what you mean by that. Because that operation is either unique, I know exactly what you mean by that because there's no other thing that you could possibly mean by that, or privileged. I know exactly what you mean by that because there's only one reasonable thing you could mean because this is the size that is most privileged. Let me give you an example. What is the len of a pandas data frame? Is it the number of rows? Is it the number of columns? Or is it the number of values? Well, this is not unique, right? It could be one of three possible answers. But in the case of pandas, we know that the most interesting thing about a pandas data frame is its index. And we know that the API strongly prefers operations that go down the rows, down the index, not across the columns. It's always a keyword argument to operate across the columns, whereas the default behavior is down the rows. So it makes sense that len of df would be the number of rows because this is deeply privileged, even though it may be potentially slightly ambiguous. In the case of a series, well, what more could it be? The number of values is the number of entries, is the number of elements in the index, the number of rows, and so there really isn't another option. And if we wanted to in pandas, we could be a little bit more explicit and ask for the length of the index versus the length of the column, but largely things like df.size, ooh, what is that? Is that the size of the rows or the columns? That one is pretty hard for us to guess. It actually means the number of values. Here, in this case, I think that there is a good argument that they've implemented len correctly on the data frame because when we look at it, it makes sense why it would be the case that this would be the number of rows. Because there isn't ambiguity, there is explanatory power because this is a privileged operation. Our next premise. We have certain expectations associated with syntax that we have. And those expectations then give us further explanatory power. Here's what I mean. If you're deep in some code and you see f called on some parameters and you don't do anything with the return value, this is probably performing an action. It probably has some consequence to the outside world. It wrote to a file, it opened a socket, it closed something. It probably has some outside effect. Otherwise, you would have captured the return value. But here, you called the function but didn't capture the return value, so it probably did something. Whereas if you saw f and it returned a value, this probably performed some computation because you cared about the result and you're going to do something with the result later. If you're looking through some code and you see d with a square bracket after it and k and you assign that to v, this is probably a dictionary that's performing a lookup with a key giving the corresponding value. If you saw x's with a square bracket and a variable called index or maybe a variable called I and it returned a value, this is probably a list that's looking up an index and returning a single element. If you saw object.a and it returned a value, this is probably doing an attribute lookup and it's returning whatever was at that attribute. Note, these expectations guide our behavior, but they may only very loosely hold. Because if you see v equals d of k, this probably is a dictionary, but it might not be. It might be a default dictionary, or it might be a counter, or it might be a chain map, or it might be an ordered dictionary. But note that even though this isn't strictly a dictionary, knowing that it probably is a dictionary, that loose expectation is actually enough to guide our behavior because in this particular case, it doesn't actually matter which of these four types it is. We should largely be able to understand what this line does, irrespective of which of these types it happens to be. There are other expectations we might have. When we see any one of these syntactical forms, we might intuitively say, that's fast. I'm not going to do d of k, and it's going to take me 2 minutes to get a result. And if it does, I think something has gone wrong. I'm going to double check that I haven't done something wrong. Whereas if I call a function could be fast or it could be slow. I really have no expectation, which means that implementing the behavior as a function does not give explanatory guidance. It is absolutely the case that we could have written this class to be very time-consuming operation on a get item, but probably somebody is going to really wonder what's going on if they do a square bracket lookup and It takes a long time to give you an answer. When we see each one of these forms, we typically think these forms are pure. They're stateless. They're not going to change the object itself. They're not going to change the outside world. That would be pretty bizarre. And we'd expect that their result is really going to be based on the state of this object and whatever key we pass in. Whereas when we call a function, we have no idea. This thing could maybe make a change to the outside world. This thing could be relying on some data that you can't see. Now, note, this is not the case even with common things like a default dictionary. Note, when you perform a lookup on a default dictionary, it does in fact mutate the default dictionary if the key existed, but that expectation is still something we rely on because it doesn't actually matter, irrespective of whether the default dictionary does or doesn't mutate itself on lookup of an entry that doesn't exist. The thing behaves the same no matter what. Now, when we look at code like this, we have certain expectations that guide our behavior, that give some explanatory power to our code. Namely, when we see this, we expect there could be an index error if we're out of bounds. And that's something that'll happen under normal operation. When we see this, we might say, okay, there could be a key error under normal operation if we looked up a key that doesn't exist. When we see this, we might say, well, there could be an attribute error, but something has gone really wrong if we looked up an attribute and we got an error, an attribute error. We don't usually check for attribute error. Whereas when we see a function, we really have no guidance. We have no additional explanatory expectations. Anything could happen. This could raise an index error, a key error, an attribute error, a runtime error, a file not found error, a module not found error. And when you look at some code and you see this, you say, oh yeah, they were worried that maybe that key didn't exist. Completely normal. But if you saw some code like this, you'd be like, okay, wait, they probably ran into this problem deep into field testing of this code, and under some weird circumstances, the attribute didn't exist, but they didn't really expect it, and they probably added this after the fact, and something weird has happened here. You don't usually do try except for attribute error every time you do an attribute lookup. Oh my goodness, it would make your code so noisy. And if you saw some code like this, you'd be like, oh my goodness, how on earth did a dictionary lookup turn into a file not found error? That is absolutely the most bizarre thing. And so, when you are using libraries for the first time and you're sitting down and you're deciding, okay, I'm going to write this. Do I put this in a try except? You have reasonable expectations that guide your behavior that, okay, I do if I'm worried that this key may not exist. But if I'm not worried about that, I don't. You almost certainly won't write every single line of code like this because you'd never be able to get anything done. These expectations give you explanatory power and guide your behavior in effective ways as long as they mostly hold. Now, one other thing to note is, for these three behaviors, there is no additional modality associated. You can't add a keyword argument to any one of these syntaxes. The grammar doesn't support it. There was, in fact, a PEP to try and add keyword arguments to these syntaxes here, but it wasn't accepted, and at least at the current day, you cannot add modalities. What that means is, when you see any one of these in code, you never have to think, oh, did somebody forget a keyword argument? Is there supposed to be a modality here? Is there supposed to be a flag that I need to pass to make this work correctly? Whereas when you see this, you get no guidance. You have no idea. Oh, maybe I need to look at the help of this and see if there's a keyword argument that I have. When was the last time you imported something from some module and you did a help on t.getItem? You don't, because it can only behave in a certain way. It's very constrained. There are ways to encode modalities in these different syntaxes, but there's no way to encode them directly in the syntax itself. In other words, if you had a modal parameter that you wanted to add to a function, you would encode the modality by just adding a keyword argument, meaning you have made this function more complex. Somebody's going to have to write a help of f to really get a sense for what this function does. But things like a pandas series do have modalities. The lookup is in fact a modality. You can look up based off the position or based off of the index. And we can encode this modality. We just can't encode it as a keyword argument. We encode it via the descriptor protocol. Or we encode it via some sort of aggregate object that we pass in, which is generally too clumsy, so people don't usually do this. But you'll see this in things like xArray. You can pass in for the selectors. You can pass in a dictionary that allows you to pass in modalities. Or you encode this modality by writing a function that returns something that performs some modality or gives you different results based on that modality. Or you use a nominal decomposition, so you have multiple properties and you choose which of these properties you want in order to get the mode that you want. Or you do something like what pandas does, and you have descriptors, and you choose via this nominal decomposition which the descriptors you want, the lock or the iLock, the cell or the iCell, if you're in something like Xarray, and you choose which of those modes you want, but you can't encode the modality directly in the syntax, which means the syntax has a very tight expectation around what it does, and it can't do anything more. It is very good guidance for somebody. Here, the other thing you could maybe do is you can encode that modality, in the type itself, and then here you can see a common pattern. You set something, you unset something, so maybe you introduce another mechanism like a context manager to encode the modality. But fundamentally, in all of these cases, you're encoding that modality separated from the underlying syntax, meaning a user who's seeing their library for the first time, seeing this code for the first time, doesn't need to worry about those modalities existed. They're not going to do a help. Like when you do a help on read CSV and you see a million different possibilities and your head's spinning and you're not sure which of them you want. With these syntaxes, the user can only really do one thing, and they have an expectation for what it's going to do. And they have a very strong expectation, and so it simplifies their onboarding for this tool. And when they need those modalities, they go somewhere else and look up those modalities separately when they're ready to do this. You can arrange the complexity of your library according to the sophistication of the user and how this user sophistication grows over time. Here is our conclusion. When we want to implement data model methods, we want to implement them where they improve understandability by leaning into the expectations that somebody has around these data model methods and maximizing the expectations that somebody can bring to this code. Here is a fake API for loading from and saving to a object data store of some fashion. And you can see there's some global state associated with this fake API. We could write a get and a set to save objects in this database as some path or to get them. And you can see this is a fine way for you to implement this with just regular old instance methods, but it gives very little guidance to our end user. They have no expectation. Is this going to be fast? Is this going to be slow? Is this going to raise an error? What kind of errors is this going to raise? Is this going to be pure or stateful? Is this going to be something where there's modalities associated, so I have to do a help of db.get to see if there's extra flags that I need to pass? And if there are extra flags to pass, okay, sure, those could be added later on after the fact as keyword arguments, but you don't really know up front, do I need to worry about those or not? And so when I want to implement these data model methods, one thing that I might think is I could use almost the exact same code, the load path and the save to path, but I could implement this under this call syntax. But this is very poor explanatory power. When you see open close parentheses, usually see perform some action or do some computation, and this is more of a lookup, so it doesn't really comport. And usually when you see call, it usually means this is some computation where any modality is a modification on how you perform that, whereas here, this additional argument is really changing between two different operations, so this is probably a bad idea. And it gets really difficult for us to implement more complicated, or it gets really clumsy for us to implement more complex modalities there. When you see something like getAttr, you say, oh, you know what? This kind of fits better. GetAttr means perform a lookup, which is what this load from path is doing. SetAttr means store something in some place. That's what this save to path means. But when we think about getAttr and getItem, we can see that there's a further distinction. In both cases, maybe our expectation, this is fast, that this is pure, that this will raise an error if something is not found or if something cannot be placed in a particular place. And that's correct. But getAttr is not the right choice here because getAttr really means a lookup on a bounded or structural entry, whereas getItem usually means a lookup on some unbounded or data entry. In other words, this usually means we're looking something up that we're pretty sure is going to be there because we're not going to check for attribute error usually, and because it has to be encoded as a valid Python name that you can actually type. It's got to be short enough to type. It's got to start with an underscore or a letter, or strictly an XID start, and followed by number scores, letters, and numbers, or XID continue Unicode characters. And so we're kind of bounded to only a set possibilities. But when you do a square bracket lookup, you can pass anything in. So this is really some kind of unbounded lookup. We don't know what that key could be. It could be anything at all. And when we think about this related to something like a pandas data frame, we know that we have two different options for looking up a column on the data frame. We can use the getItem or the getAttr. But it's often the case that when we use the getItem, we're kind of implicitly saying this is some data that the data frame contains, and that column may or may not exist. And this is saying this is something that the data frame has to contain for it to be valid. And this is more of some structure we're pulling out. Now, who am I kidding? This is because we're data scientists and we're too lazy to type the extra characters to write this. But when we see this applied to our object data store, we can see that this is actually probably the best way for us to implement this API. It is in fact a good idea for us to use getItem and setItem here because it gives us a lot of explanatory power. This is a lookup. It's an unbounded lookup on some data, namely the path. It is a lookup that's going to be fast. It's going to look up that's going to error in certain ways if the thing cannot be found or the thing cannot be placed. It's a lookup that's not generally stateful outside of changing, obviously, the state of maybe the object itself here, which is what this will do. And it's something that is really determined mostly by the state of this object and the state of, and the arguments that you pass in. And it leans nicely into our expectations. And when we want to add modalities to it, we can separate out those modalities in some advanced functionality. We can write a context manager or we can write a descriptor. In order to implement the advanced modes, we can still pass in a timeout or pass in a dry run mode. But nicely enough, the simplistic use case is now separated from the complex use case, from the advanced use case, meaning our users have an easier time using this code. Now, one interesting thing, there's a little bit of sleight of hand here. One of the things you might say is, well, if this is an object store lookup, maybe it's going over the network, so maybe it could fail for all sorts of Byzantine reasons, DNS lookup failures, or maybe it's not fast. Maybe it could take on the order of microseconds or even seconds if there's some sort of network outage. Here's my counterpoint. If you cared about those two cases, you would never implement this code with direct access to the storing and the retrieving. If you cared about things like network disconnection or the speed of this, you would really write this as an API that managed underlying requests so you could schedule them when you wanted to schedule them and you could deal with things like retrying things. You would never have written it like this in the first place. That you wrote it like this in the first place is actually because you're implicitly saying this is fast enough and safe enough that I don't need to write a request-based, an API that indicates, oh, schedule these things and then execute them. I don't need to detach those two pieces because if you really needed to handle that, how you handle all of those kind of errors, the slowness, the timeouts, all of those kind of things, or the slowness or the unsure timing of this, or the Byzantine errors, well, all of that's going to be some sort of ad hoc behavior that's going to introduce a lot of churn because a lot of different people are going to want to handle it differently, and an API like this would never be able to handle it in the first place. You'd have to write an API that surfaced all of those elements. You'd have to write an API that looked more like db.createRequest, and you create a request, and then in your API, you schedule when you want these to run, and the API would look quite different.